Hello class, welcome to week 11. So any week that we have quantitative analysis techniques, we'll have a video for you, and this will actually be the final video that we have for you for this class. So we're moving right along. Inferential statistics is probably one of the more complicated components of this course, but fear not, I aim to keep this largely simple and conceptual for you, so you don't have to worry too much about doing any kind of math, but you still need to understand the concepts so that as you're reading your articles, you have some kind of an idea of what they're talking about. A lot of your research articles tend to be quantitative in nature. That's just kind of the nature of a lot of the published articles because they have pretty good external validity. So inferential statistics, at least in understanding some of the terminology, is going to be important. You won't be able to get it all in this class. We just don't simply have enough time for that, nor do we really have a need for it for you to understand everything. But hopefully you can get a few of the keywords here and kind of understand what some of them are. So when you do read your articles, you can interpret what they're saying. So on our discussion boards this week, we'll begin with our 3-2-1 exercise and just review from last week, and please feel free to let me know if you do have any questions that remain from last week. So this week we'll cover only inferential statistics, only a couple of discussions this week because it can be a fairly complicated thing to understand, so we'll do our best to just kind of focus on just the inferential stats this week in terms of just your jigsaw and then your understanding of inferential stats as well. So going back to a couple weeks ago, we talked about descriptive statistics and inferential statistics and the difference of those. So in chapter 3 for the book, first half of the book is descriptive statistics, and then the second half of chapter 3 covers inferential statistics. The difference really between them fundamentally is that the descriptive statistics would only cover, we talk about research, and what we do with research, you recall that we can only sample, we can't get data from our entire population. So descriptive statistics are usually just going to be I apologize for the writing there, a little hard to write on an electronic screen, but descriptive statistics are going to apply only to the sample. And then inferential statistics are when we take the results of what we got for data from that sample, and then we infer them back onto the entire target population. So that's the purpose of descriptive versus inferential statistics. And that's what we're learning here this week. So the first concept, we talked a little bit about correlation previously when we talked about, when one variable changes, another one changes. An example we used previously was, the more hours that you study for this class, the better your grade is going to be. And that's a simple correlation. So when we have a positive correlation, these are called scatter plots. And basically what a scatter plot is anytime you have data that you're gathering from your sample, you're going to be plotting that out. And so we can, load all that information into a statistical software like SPSS, or we can use Excel, and then we can create some charts just so we can plot it out and see if there is a correlation between our independent variable and our dependent variable. So in our X and Y of the chart here, that would be we're plotting our independent variable on one end and our measure of the dependent variable on the other to see if there's consistency between, as one goes up, the other one goes down. So, for instance, the number of hours that you spend studying, that would be our independent variable, and then our dependent variable would be the score on your final exam. And so the hypothesis would probably be that the more you studied, the better you did on your exam. And so that's how we plot that out in terms of a correlation. If we have a negative correlation, for instance, what we would use for our independent variable with that one, we would say that maybe the number of hours that you spent socializing during the semester might work against your overall score for the exam. So so essentially, the fewer number of hours that you spend socializing would be necessary to get a higher score on the exam. And so they would be inverse of each other, and that's what we would have for a negative correlation. So the positive correlation is a number that ranges anywhere from 0 to 1. The higher the number that is, the stronger the correlation. And if we have a negative number, it means that we have an inverse correlation. So, the fewer number of hours that you spend socializing during the semester, the higher your exam score. Again, that's just a hypothesis. But in this case, maybe our data would actually demonstrate that. So if we have a strong correlation, it means that why we call this a linear regression is we're looking for the existence of what appears to be a line. So as, if there's a strong linear correlation, it means that, as one goes up, the other one goes up, basically, for the most part in, a direct response to the other one. And if we've got a strong linear correlation the other way, obviously you've got the opposite happens. But the higher the number basically means that your data are more representative of a line. So as you get closer to 1 or -1, it means that your data are very, very strongly correlated in a way where they start to look like a line when we plot them out. On the other hand, when we have a moderate correlation, it's something that's around 0.5. The data, when we plot them out, they're not so exactly connected and correlated to each other. And when we have a weak correlation, which anything below, I believe, like a 0.2, you'd have a weak correlation, and maybe whatever we have for our hypothesis doesn't necessarily hold true. So the more they have this linear trend, we can say that there's a direct correlation between the two of them. We consider it to be a regression then. When we talk about descriptive statistics versus inferential statistics, we also would use statistics, and the word probability comes into play with inferential statistics in the probability that, for instance, if I knew you were spending X number of hours studying for this course, that you would have X score. So I'd say if you spent half the amount of time that you needed in this class studying, you'd get a score of about 50 on your final exam, or if you had spent enough hours, you'd get 100. And so that's the difference between the correlation, which is basically just the descriptive statistic version of just plotting that data out once we get it, but we can actually then use it in a regression format with probability to say that if I know how long you studied for, I can predict your score in the final exam. And the stronger the correlation, the greater the ability that I could then predict your score in the final exam based on how long you studied for the class. So that correlation coefficient is usually reported as an R value. So it's this thing up here. It's actually a small r, but based on the font that I have here, it actually came up as a big R, but it's actually a small lowercase r. And so again, that's going to range anywhere from -1 to +1, depending on whether you have a positive correlation or an inverse correlation. So R value on the other slide was a -0.89 if there was an inverse correlation. And that could be just about anything, again, ranging from 0 to 1 or 0 to -1. That would be for parametric data. So there are, when we do statistics in research, there are two different main types of statistics. So we have either parametric statistics or we have non-parametric statistics. With parametric statistics, the assumption is made and applies when we look at that data. So you recall from back in previous weeks in the first half of the semester when we talked about descriptive statistics, we looked at this bell curve thing. Okay, so the bell curve is basically a description of the data that we collect, and it tends to have this bell-shaped kind of thing that happens. And that's what we consider to be a normal data set, or a normal curve. And that data, under most circumstances or in ideal circumstances would look just like this, and would have all of these, perfect, look like a perfect parabola, and it would, be really, really nicely laid out, and everything's perfect and average. But that, in reality, that's just not the case. So, if our data are close enough where they resemble this standard normal bell curve, we could then use what's called parametric statistics, because, the word parametric basically means it's equal, and, it's synonymous with a perfect data set. Non-parametric data would be used in a case where when we get that data, we look at it, and all of a sudden it's like, well, boy, that doesn't look perfect. So you may have, a case where your data are something, shaped something like that when we do our histogram, or they might be shaped on the other side, or you might have, a couple of, I call bimodal data, where there's, a couple of different sets of data that were actually kind of overlapping for some reason. So it just kind of depends on the data that you have and the type of statistical test that you use. So the Pearson correlation is, there's this Pearson guy that came up with the original concept of correlation coefficient, and they named the statistical test after him because that tends to be the way that things are done in mathematics. You use the person's name, whoever invented the concept. So the Pearson correlation is for parametric data, and then this Spearman guy came along a few years later and said, well, what if we have this data that it doesn't represent this normal curve? And then he came up with all these formulas and stuff for non-parametric data sets, and that's basically the difference between parametric and non-parametric. So if you see those words used in your research and your study, you know that basically just that the data aren't perfect, and there is no such thing as perfect data. So it's just a matter that they are trying to use the proper statistical procedures to analyze that data correctly. And then we talked about the linear regression again, the fact that it's a line. When we look at those plots, that's a linear regression. So just kind of keep that terminology in mind. Hopefully that helps you visualize and conceptualize your data and what they're talking about in your study. So probability and significance. Essentially, when we do hypothesis testing, where we get that data, this Pearson correlation, when we then talk about inferring that into the inferential sample with our correlation, we talk about the probability of that differing from the experimental and control group. So when we do our study, we have this hypothesis that says we think we're going to find this, whatever that means. So, if let's say the hypothesis for this class is that if I thought the more hours you studied, the better you do on your post test. So I could certainly have experimental group and control group, and I could have one class that we just made everybody study a lot and spent a lot of time studying, and then another group where you just said, okay, you're not allowed to study at all, and we'll see if there's a difference between the scores. The level of significance would be reported then when we examine that hypothesis and conduct the analysis. Generally, it's going to be a p-value equals a certain level, and that level actually is going to be kind of the inverse of the correlation number, because with the level of significance, the smaller the number, it means that there is a higher likelihood or a lower likelihood that your data are going to be, predictive of whatever that actually is. So if I've got a p-value of, usually what's going to happen is you've got a p-value of 0.5 is kind of the level that's set up, and that's what we call an alpha level. The p-value, as it gets smaller, so that ranges again from 1 to 0, actually it never really hits 0, so it gets 0.0001. The smaller that number gets, it means that we can say, with reasonable certainty that whatever our hypothesis is, that we're predicting that one caused the other, essentially, in our research design. So the alpha level is kind of what statisticians say is the level where we're going to say that, okay, if P gets smaller and smaller, so let's say P was, 0.5, that wouldn't be small enough. This would be kind of like our bar for what we're going to say is that, okay, anything below this amount, we're going to say that we found support for our hypothesis, and we're then going to reject the null hypothesis. So we never, in research, as you recall from some of our discussions this semester, we never actually prove anything with research because there's always the existence of an extraneous variable. That's why our p-value never gets to 0. It gets close, but it never can really quite get there because we never can say with 100% certainty that what our research is telling us is we've completely found, this thing, and it's going to hold true every time, because there may be something that happens. We've only conducted research on a sample of people, for one. That's one reason that we can't say that with 100% certainty that we've proved anything with our research. Maybe just a snapshot in time. There may be something within our study that if we repeated it later on that it wouldn't hold up. So we never prove with 100% certainty. And it's kind of like I guess the best way to look at this is that the p-value is more or less kind of the how much uncertainty is there in our findings. So a p-value of a 0.05 would basically means that, well, there's about 5% uncertainty in our findings that, that we said we found this, we looked at the data, but there's still a little bit of a margin for uncertainty. P-value of 0.01 then would mean that we're about 1% unsure that whatever it is that we thought it was and what we concluded, that there's 1% chance that there's some kind of a variable out there that we didn't recognize or whatever have you. And then you may have a p-value of like a 0.001, which means that we're about 0.1% unsure. So it's basically our level of certainty in our research that that we can say that we have found data to support whatever our hypothesis is. So that's important because that number, that p-value, will get smaller and smaller and smaller, and you'll have a number of decimal points that'll go out 5 or 10. Never actually find where your p-value is actually 0 because we've got that extraneous variable. So that's the importance and the reason for why we have this concept of the null hypothesis versus a hypothesis, because the hypothesis says we're going to find something. The null hypothesis says that we're not going to find something. So it's basically the inverse of the hypothesis. The reason we can never actually prove a hypothesis, when we have a hypothesis, okay, we can never say that we're going to prove it because we just never have enough data to do that. On the other hand, we use the null hypothesis to say that, well, the null hypothesis is the opposite of that. It says that we're not going to find it. Well, we can reject the null hypothesis because we have enough data to say that, well, that probably isn't true because we're 99% sure that that's not the case, but yet we're not 100% sure enough to say that we have proven our hypothesis. So that's the difference between a hypothesis and a null hypothesis. The alpha level is, we may have a little small letter a. That's basically this, and that's going to be the level that's set by the researcher of okay, how certain do we need to be, and how much error can there possibly be in our data, where we're going to say, okay, are we 95% sure about this thing? It's close enough. Or do we need to be 99% sure? Or do we need to be 99.9% sure? So that's what the alpha level is the researcher saying, well, I think if we're 95% sure, we can say that we're pretty good. And that tends to be that p-value of a 0.05, which equates to 95% certainty. That's the generally commonly accepted alpha level, meaning that if researchers say and statisticians say that if we're 95% sure of something, we're pretty sure, and from a research standpoint, it means that we found something that's pretty significant. And that word significant or statistically significant means that we're 95% sure, or whatever it is that we use for an alpha level. Whereas a researcher might say that, well, I think it's important that we want to be 99% sure rather than just 95% sure. That's really kind of an arbitrary thing. There isn't anything that really dictates that, other than, with some more complex statistical analysis tools, they may say that, well, we would want a 99% certainty. At any rate, the more certain you can be of your test results, or of your results of your research, the better you're going to be off. So it means that there's less error in your overall research study. So in a nutshell, that's the basics of that. So linear regression and multiple regression, basically the difference between the two of these. This stuff will all be reported in terms of p-values and R values, as we talked about previously. So as you're looking at your data, these are pretty common. Linear regression, again, hopefully understand. The concept here is that what we're doing is we're saying how with what certainty or level of certainty can we predict, if we've got one variable or independent variable, can we predict the dependent variable, and how certain are we going to be of that? The multiple regression is basically the exact same thing. It's just that we're probably going to have, we will in this case have multiple different variables, and then we can use, let's say we have identified multiple different variables that we think are going to be predictive of your dependent variable. We can sum all those things together and say that, well, between these 4 or 5 variables, whatever it is, then those all of those things combined are going to be predictive of our dependent variables. So a linear regression, a simple linear regression, means we have one independent variable is going to be predictive of our dependent variable. Multiple regression means we are probably going to have maybe 1, 2, 3 independent variables. And all of those then are going to be needed to be predictive of our dependent variable. So we might have multiple different things that we're measuring, and altogether they equate to predictability in our one dependent variable. To understand the difference in those. And in order to demonstrate that in a descriptive study usually, although certainly structural equation modeling could be used in other forms of data analysis as well, or research designs as well. Typically it's going to be used in just descriptive studies, but structural equation modeling means that equation and that kind of that visual image that we talked about previously. We'll look at here on an upcoming slide. The structural equation modeling is basically the way that we think we're going to just visually map out all that data and those variables that we're testing, and we'll analyze the factors that are involved. So basically a factor analysis, we're looking at the different variables that we conceptualized and that we hypothesized that all of these different independent variables are going to be linked to our dependent variable in whatever way. And so we use statistics in the form of structural equation modeling to then validate the way that we thought that those things were going to have a predictive relationship of each other. So we're using this then to test the theory that we have. So this is an example of structural equation modeling. This is the concept that I used from the video a couple of weeks ago. Structural equation modeling is, we've got a bunch of independent variables here. and a couple of dependent variables. We're going to say that we think that all of those variables are necessary to kind of act together to draw a linkage or to in the cause-effect relationship here between our independent variable and our dependent variable. We think that all of those things need to be there. So it's a visual representation of what we think is actually going on in our behavioral research design. And structural equation modeling is the way that we then communicate all of that. We do a bunch of statistical analysis. We analyze all of those relationships, and we then report that in the findings of our article. And structural equation modeling is something you'll probably see quite often in a lot of your articles for this class. So that's structural equation modeling. Okay, now we'll move on to t-tests and ANOVAs. So the structural equation modeling and some of the things that we talked about already to this point are if we have a research design where we're talking about correlation. So with a correlation, one thing goes up, something else goes up or goes down, depending on whether it's a positive correlation or a negative correlation. And all those tools are generally used to define the concept of correlation and not causation. When we get into the t-test and ANOVAs, which we'll talk about in the upcoming slides here, we begin to go from correlation, which is used more often than not in your descriptive studies, to causation, which is used more in your experimental studies. So pre-experimental, quasi-experimental, but then true experimental would utilize these types of causal inferential statistics. So you'll recall from when we talked about the true experimental research design, for instance, or any of the experimental designs, a lot of times we're looking at group differences. So we want to say, is there a difference between our experimental group and our control group? So with the t-test, we gave it the letter T for whatever reason, what we're looking at is the difference between our experimental group and our control group. And these bell curves, so we've got the descriptive bell curve that we used in our first half of the semester to talk about descriptive stats. What we do is we take a look at that data, we put it in a bell curve, and then okay, we know what that data is and what the data looks like. What we would do then with a t-test is we would then compare one data set, population 1, sample 1, to another data set, our experimental group and our control group. Okay, so we're using statistical techniques and the descriptive data then to compare them to another to see if there is enough difference between the two of them where whatever we did within our research design caused the one thing happened to one group and one thing happened to another group, and so there's enough difference between the two of them to warrant that. Another way we could apply that for let's say for the purposes of this class, a simple t-test. We'll get rid of the whole experimental control group. Let's take a look at maybe a pre-test and a post-test, like we're using for your for this class. So when you started out before week 1, you didn't know anything coming into the class, you took a pre-test. And then our final exam for the class is what we consider to be a post-test. So in between there, you hopefully learned something where you spent the last 14 weeks learning all these different terms, reading the book, doing the discussions, doing the assignments. Hopefully you've learned something between the pre-test and the post-test. And so what we'll do at the end of this class, and what I've done with every class, just to demonstrate that you've actually learned something, is we'll do a t-test between those scores that you got for your when you first started and you didn't know anything coming in. If you recall, the average test score, out of 0 to 100 possible was somewhere around a 20. Okay, so you got a 20 when you came into the class. My hope would be that you're going to have probably something about 95% or above. Hopefully you're closer to 100. But my goal is to get you all at an A by the time you leave the class. And if I compare the results of the pre-test score to the post-test score, those scores are so different that we can say that whatever happened between week 1 and week 14 caused you to actually learn something in the class. For whatever happened in that 14-week time frame, you learned something. So that's an example of a simple t-test. But we could also certainly use that same concept for different groups. We could have an online group, we could have an in-person group, and compare the differences between the two of those. You can have one group that just didn't take this class and compare their results on the post-test to your results after you took the 14 weeks and see if there was a difference. So depending on how we set up our research design and our question, that's how we would use our data analysis technique then to demonstrate whether we've found evidence to support our hypothesis. Then we use something called an ANOVA, and an ANOVA is the analysis of variance. That's what that acronym stands for, analysis of variance, to see if there was a variance between those groups. So let's say that my hypothesis for this class, being that this would be a blended live class if we conducted it that way, we've maybe got the samples that we've got here. We would try to hopefully infer the results that we have out of our samples in this class to a larger population. But let's say that we wanted to compare our online group, your post-test scores, to an in-person group who took the class. And then we would want to do ones that attended with the blended live web conferencing. Apologize again for my writing here on this electronic screen. But so we could then use an ANOVA to look at those multiple different groups to see if there's any difference between them, and we'd have multiple groups that we could use as many as you'd like with an ANOVA. So the ANOVA uses 2 or more groups and does a group comparison. We have an experimental group and a control group, or whatever our research design is, and then we've got one independent variable. So what we're doing is we're just looking at the independent variable in this case would be the completion of the class, the 14-week class, CN734. That would be our independent variable, and that 14 weeks that you spend in the class. And the dependent variable then would be our post-test and your final exam for the class. So we're just comparing the multiple different groups, introducing the independent variable, and then seeing if you learned anything in the class on your dependent variable. A MANOVA stands for a multivariate analysis of variance. So, let's say that we wanted to look at 2 dependent variables then. So in the case of your pre-test and post-test scores, in this one with the ANOVA, which is just an analysis of variance, a multivariate analysis of variance would have 2 different dependent variables. So we're going to look at the post-test, and then maybe we're going to look at your satisfaction with the class as another variable. So you took the class, which is your independent variable. We had a couple of different groups. We had an in-person group, we had an on-person group, or an online group. We compare the difference between 2 of them, or we may have an experimental group, control group. However we set those groups up, you took the class, it's your independent variable, and then we're looking at the dependent variables and the outcome on your post-test score and your satisfaction with the class. That would be a multivariate analysis of variance. So multiple variables. Let's say that then we found that there might be something that, for whatever reason, we thought was going to have an effect on your performance in the class or your satisfaction with the class. Then we look at something called a covariance. So an ANCOVA stands for analysis of covariance. So we're looking for an extraneous variable that we want to control for. So let's say for the purposes of this study that that I identified that okay, maybe there was perhaps some kind of correlation between how much time you spent studying and or your the number of hours you spent working. So if we want to use your work hours as an extraneous variable, so those of you that are maybe working full-time or working more than that, we'd want to test to see if, regardless of how much time you spent working, We can then, within our study, find out what your average number of hours that you spent working in the class to see if we can then control for that in some way. We can either control for that through the the setup of the design, which is going to be preferable in some way, where we say, okay, we're not going to let people who take the class that are working, but in reality, that's probably not going to happen. So we would control for that statistically within all of our formulas and all of our equations by just simply asking you, okay, how many average hours on when you took this class did you work? And then that way we'd be able to control for, well, was it actually the class itself and the learning and everything that happened here, was that what contributed to your learning for the class? Or was it the work hours, which may have kind of served as a drag on your learning, which certainly could be the case. And then the Mankova version of that is, same exact thing as the difference between our ANOVA and our MANOVA, being that it's a multivariate. So we've got the two different dependent variables. So in this case, we could look at your post-test score, and then your satisfaction with the class as being your two different dependent variables. And then, how many hours did you spend working? We want to make sure that we just control for that statistically as our extraneous variable. So that's kind of research design. And I've got a handout that I'll put in the folder this week for you so you can kind of see all these different designs and kind of help think about all that. It can blow your mind, it really can. And so hopefully some of these examples that I've talked about here help you understand this stuff, but it just kind of comes down to the number of groups you have, the number of variables you have, and if you have extraneous variables, what statistical techniques that you're going to be using. But essentially, ANOVA, MANOVA, ANCOVA, MANCOVA, they're all kind of doing the same thing, in that we're just looking for differences between if we did some kind of either a pre-experimental, quasi-experimental, or true experimental study, we're looking for group differences in our variables. It's just a matter of what variables we're kind of looking at. So hopefully, once you see some of those terms, you know that we're looking for group differences in some way. Okay, so that's quantitative analysis. Qualitative analysis is a little simpler, and typically what's done in qualitative analysis. So if you've mastered up to this point and you followed along for the first 35 minutes or so of this video, that's inferential statistics in a nutshell, and that's everything you need to know in terms of getting most of published research and understanding the methods and results sections of your quantitative analysis. Qualitative analysis is a little bit more, it's based on words. So qualitative studies, again, you're doing a lot of interviews, you're doing focus groups, you maybe use any of those different techniques to gather your data, but you still have to analyze it in some kind of a logical way. And the way that we do that is using the concept of coding. So with coding, what we do is we may find that, okay, so how I developed the survey for this class, and I would go out and I would talk to students. I would say that, okay, well what makes you satisfied with your class? Or what do you think helps you learn in the class? And I would go out and talk to a bunch of students, and they say, well, it's important that I have a good syllabus. It's important that the instructor is really engaging. It's important that they do a good job of explaining things, or have a good textbook for the class, or an instructor responds to my email communication in a timely manner. There's going to be a lot of different things that that if I was going out and doing interviews with students, that I would say are going to contribute to your learning for a class. With content analysis, then I would gather all that data. I would take all those interviews. I would transcribe all of that, all those interviews. So, which means I would sit down and I would type them all up into a Word document or what have you. Or I would handwrite everything all out. And so I would take all of those interviews, and then I would want to turn interviews into data in some way. So essentially, we start out here with just words at the bottom of the pyramid, and then we work our way up into themes that we're going to get out of all of that. So we start out with the words, raw data, begin with all that raw data, and through various techniques with sifting through the information, it just kind of takes time. And We generally call this constant comparative in the coding process. What we're doing is we're starting out with some categories, and so we're beginning to put our words into different categories. And so whether regardless of what our interview said, we're going to have maybe 5 or 10 different categories of data that we'll talk about here first. And so the words, we're going to start to group everything together, and then put everything in different categories. And then we may have 5 to 7 categories as we go on up, and we've looked at things and said, okay, there might be some things there, or we may have more categories depending on the complexities of the data. And so we're just going to kind of keep, maybe we break this down to 3 or 4 different main categories, and then with each one of those, you're going to have a bunch of different categories underneath them. So we're just organizing our data. The visual example that I tend to use for coding and how it works is kind of like if I gave you a bag full of M&Ms and Skittles and Reese's Pieces, and within that bag full of little like-shaped types of candies, and I might throw some different candy in there as well to really throw you off. I'm going to give you a bag full of candy, and the bag full of candy, your job as a researcher then is to sift through that bag of candy and start organizing the candy into different like types of candy. So you might have all your M&Ms in one pile. You might then put all your peanut M&Ms in another pile, and then you're going to take all of your Skittles in another pile, all your Reese's Pieces in a different pile. And then I might throw in different, like I said, I'll throw in Snickers bars in there, and throw you for a loop. But what you're going to do is you're going to take all of that stuff, whatever it is, if it's candy, if it's words, you're going to organize everything into different groups. And then eventually you kind of start to see themes in your data, and you see that, okay, we've got a bunch of M&Ms, and even with our M&Ms, we could say we've got red M&Ms, we've got green M&Ms, we've got brown M&Ms. We code our data and start to organize and categorize our different pieces of candy that were in that bag, and into all of our different themes. And at the end of the day, we could produce one report that says that we have X number of M&Ms, we have X number of Skittles, we have X number of Reese's Pieces, and within those we've got, okay, X number of red ones, green ones, brown ones, so on and so forth down the line. So what we're doing is we're just summarizing the data that we've received in all of the kind of the raw words that we received back from our qualitative research, and we're just organizing that into themes. And that's the concept of data analysis for qualitative research. And we're just kind of grouping things into different themes and categories. So I hope that makes sense as far as what you would do then in a qualitative study. And if any of the studies that you have are qualitative, hopefully you can kind of see this process following out, or if you're going to be considering conducting qualitative research for your research proposal, you can kind of describe this process then there, of how you're going to then gather and organize your data in data analysis. So qualitative data analysis can be certainly very time consuming as well. It can take a long time to take all those words and transcribe them and organize them. Not as straightforward many times as inferential statistics can be, or descriptive statistics can be, because there aren't as established principles for that. But nonetheless, very important that there is some type of procedures used in analyzing your qualitative data. So discussions for this week then, you've got your inferential stats. So break it into descriptive statistics terms and inferential. Hopefully you can kind of delineate between the two of them by now. Again, descriptive statistics are the ones that describe the data, and inferential statistics are the things that we talked about today that are going to be inferring onto larger populations. So descriptive is the first half of Chapter 3. Inferential is the second half of Chapter 3. And then, are there going to be things that you're going to find in there that you don't understand, that we didn't talk about here? So we've given you basically the very basic knowledge that you need to understand descriptive and inferential stats in this class. And hopefully you can kind of limp through your articles and see a few things that make sense in there. You're probably going to find a bunch of junk in your article that isn't going to make sense either, and that's totally okay. All right. So you know, if you see something that doesn't make sense, if you have any questions on it, you know, please feel free to ask. You know, I may not be the all-knowing when it comes to all stats, because sometimes researchers are, you know, doing some crazy things with statistics, and you know, sometimes there are things that are rarely used that are reported, or might be a new technique. So I don't claim to know all the answers, but hopefully we can at least get you the basics of some of your inferential statistics and descriptive statistics. And you got a lot of terms here that you learned this week. So a big chunk of your knowledge came off of the weekly discussions here, off of your chapter 4. It's important, though, I think, because you have to understand some of this stuff, because there's a lot of statistical terminology used in articles today, and while the book doesn't do a real good job of it, hopefully this video this week helped you kind of understand why some of that stuff is important and how to use it. So so go ahead and post on your note check for this week, and hopefully that contributes to your learning for your post test. So if you have any questions at all, feel free to let me know. Happy to help out in any way. We'll see you on the discussion boards.